Today we will start with a new topic which is very important and essential part for designing sequential logic circuit, that is state reduction. Any design process must consider the problem of minimizing the cost of the final circuit. That was our one of the targets since we started designing the combinational logic circuit. The two most obvious cost reductions are reductions in the number of flip-flops and the number of gates. So in order to reduce the number of gates and the number of flip-flops, we must reduce the state table or state diagram if possible before designing the sequential circuit. Let me illustrate the need for state reduction with an example. If we see this state diagram, the states are represented by A, B, C, D, E, F and G, where A is the initial value and A can have 0, 0, 0, B can have the value of 0, 0, 1, C can have the value of 0, 1, 0. In this way we can assign the corresponding state values, but these are the notation for the corresponding states, as the numerical number is not that much important for reducing the state. That's why they are represented by A, B, C, D, E, F, G. Here the input sequence and the output sequences are important. A is the initial state. When the circuit starts at the reset condition, it will start from A. At that moment, if input is given 0 value, the next state will again come back to A by giving output equal to 0. In this way, we can demonstrate the complete state diagram. Here we may have infinite number of input sequence that may be applied to the circuit. Each result in a unique output sequence. That means for any unique input sequence, we'll get a unique output sequence. Let me give you an example. Suppose for this state diagram, the initial state is A and the input sequence we are providing 0, 1, 0, 1, 0, 1, 1, 0, 1, 0, 0. This is the input sequence we are providing. So if this input sequence is given, first input will be 0, in the next clock pulse the input will be 1, in the next clock pulse the input will be 0. In this way it will proceed. So let's tabulate the state, present state, input, and what is the corresponding output and what will be the next state that will be written in the state row. So first of all, we have given an input of 0. So if input 0 is given, what will be the next state? Next state will be A and the corresponding output will be 0. So being at A, if input 0 is given, the next state will be A and the corresponding output will be 0. Now again we are at A. At that moment, if input 1 is given, what will happen? If being at A, if 1 input is given, then the next state will be B and the corresponding output will be 0. So being at A, if 1 input is given, the next state will be B and the corresponding output will be 0. Again, being at B, if the third input is given, that is 0 input, then what will be the next state? The next state will be C and the corresponding output will be 0. So being at B, if 0 is given, corresponding output will be 0 and the next state will be C. Now being at C, the fourth input is given, that is 1. Being at C, the fourth input, that is 1. If 1 is given, then the next state will be D and the corresponding output will be 0. So next state will be D and the corresponding output will be 0. Being at D, if the next input is given, what will happen? Next input is 0. So being at D, if 0 input is given, it will go to E state giving an output of 0. It will go to E state giving an output 0. Now being at E, if next 1 input is given, the next state will be F and the corresponding output will be 1, that is written here. In this way we can keep plotting our table and we'll get what is the next state and what is the output sequence. Here for any input sequence we are getting a particular output sequence. Here in this table, in each column we have present state, input and output. The next state is written on the top of the next column. In this way the output has been written. Now we will reduce this state diagram in a way. For this state sequence, if we get the same output sequence, we will be able to say that reduced state diagram is equivalent to this state diagram, because both of them are giving us same output sequence for the same input sequence, same output sequence for same input sequence. It is important to realize that in this circuit the states themselves are of secondary importance, because we are interested only in output sequences caused by the input sequences. In order to start the state reduction process, first we need to plot the state table for this example. This is the state table for the state diagram that is given here. If the present state is A and input x equal to 0, then the next state will be A. Present state is A, input x equal to 0, next state will be A, and corresponding output for x equal to 0 will be 0. If the present state is A, if input x equal to 1, the next state will be B and the corresponding output will be 0. By now, from the knowledge of previous lectures, I hope you will be able to produce this state table from the state diagram. This is nothing but another representation of this state diagram. So go for each state. If the present state is B, then what will be the next state for x equal to 0 and x equal to 1, and what is the corresponding output for x equal to 0 and x equal to 1. In this way, if we keep plotting, we'll get this state table. Here from the state table we can see we have 7 distinct states: A, B, C, D, E, F, G. Now remember, 2 states are said to be equivalent if for each member of the set of inputs they give exactly same output and send the circuit either to the same state or to an equivalent state. What does that mean? Let me show you the case from this example. For any set of states, if we get next state for all input combinations and output for all input combinations are same, then we can say these 2 states are equivalent. For example, here we can see we have E state is having next state A and F for x equal to 0 and x equal to 1, and output 0 and 1 for x equal to 0, x equal to 1. Again, G is having the same thing, same next state A and F for x equal to 0 and x equal to 1, and output A 0 and 1 for x equal to 0 and x equal to 1. So these 2 lines are same. These 2 lines are same. So we can say E and G are equivalent state. So instead of writing G everywhere, we can replace that G by E, because E and G are having same type of states for all combinations of inputs. As state E and G are equivalent, one can be removed. Here in our case we will remove G, and instead of G we will write E everywhere. So we will remove G from here. So here we have G. G can be replaced by E because G is equivalent to E. G is cut here, and we will write E instead of G. So this state is F, E, F, 0, 1. The state change of F will be from F to E for x equal to 0, from F to F for x equal to 1, and the corresponding outputs are 0 and 1 for x equal to 0 and x equal to 1 respectively. Now let's start checking again whether we have the previous type similarities for other cases or not. Here we can see if the D is the present state, for x equal to 0 the next state will be E, and for x equal to 1 next state will be F, and for x equal to 0 the output will be 0, and for x equal to 1 output will be 1 respectively, and we are getting the same next state and same output for both the cases. So we can say these 2 states are equivalent. One state can be removed. We'll remove F, and wherever we have F, that will be replaced by D, as D and F are equivalent. So F will be removed, all the F's will be replaced by T. Now let's check again whether we can reduce more states or not. Now we do not get any other similarities. Here we have AD, but here the output pattern is 0 0, but here the output pattern is 0 1, so we cannot remove these, or we cannot say these two states are equivalent. This is the final reduced state table. How many states are there? A, B, C, D, E, and the corresponding states and outputs are shown here. So F and G states are removed and they are replaced by this D state. Next, if we draw the reduced state table, it will be looking like this: A, B, C, D, E, and the next corresponding next states. From here, if we draw our state diagram, the state diagram will look like this state diagram. Now, this is the reduced state table and state diagram from the original state diagram. If we implement this problem, definitely this will take less number of gates than the state table and state diagram shown in the previous slides. In this way, we can reduce our state before we implement a sequential logic circuit. Till now, we have learned to design a sequential logic when the problem statement is given. We started from developing the state diagram and state table, then ultimately we found out the circuit. What will happen if we need to go opposite? Like a previously designed circuit is given, we need to know what is the characteristics of that particular sequential logic circuit. In order to know, we need to analyze that previously designed circuit. Let's give an example so that the idea becomes clear to all of you. This is one of the previously designed sequential logic circuits designed using 2 D flip-flops. There is input X, output Y, and 2 state bits A and B. Both the flip-flops are fed from a same clock pulse source. Every clock pulse triggering, the states will be changed based on the input given here, and the corresponding output will be found out here. Now, what is the characteristics of this sequential circuit? What is the state diagram and state table? In order to find out that, we need to analyze this circuit. How to analyze that? First thing we need to do, we need to find out what is the input equation for each flip-flops. We have one input for D flip-flop and for T flip-flop. Here the D flip-flop is used, but remember, if you'd use JK flip-flop and RS flip-flop, then there would be 2 inputs for each flip-flops. Here we have one input. So for each flip-flop we will get only one input equation. Here one input equation and here another input equation. But remember, if the designing is to be done using JK flip-flop or RS flip-flop, we need to have 2 input equations for each flip-flop. Now, what is the input equation for the first flip-flop? That is A flip-flop. We are considering this A flip-flop. In order to get the input equation here, we need to know the inputs of this OR gates. So what is the input here? That is the output of this AND gate and this AND gate. The output of this AND gate is, one of the input is X and another input is coming from A. So this is X and A, the output of this AND gate. And the output of this AND gate is X and B. So X and B will be the output of this AND gate. So what is the input here? The input of this flip-flop is XA or XB. Similarly, we need to find out the input of this D flip-flop. What is the input of this flip-flop? That is X and A prime. So I can write DB equal to X and A prime. What is the output equation for this circuit? Output equation for this circuit will be something like this: A or B whole ANDed with X prime. So these are the governing equations for this sequential circuit. Now we need to develop the state table and eventually state diagram for this circuit. In the state table, we will have present state, input, next state, output, and these are the columns for excitation table. So we are keeping it here. So present state and inputs combinations can have these values 0, 0, 0, 0, 0, 1, 0, 1, 0 in this way up to 1, 1, 1. Now when the present state A equal to 0, B equal to 0 and input X equal to 0, first of all we need to find out what are the inputs for first flip-flop, that is DA. DA is the input for first flip-flop here, and the inputs for second flip-flop, that is DB. DB is the input for second flip-flop, that is here. So if we have A equal to 0, B equal to 0 and X equal to 0, what will be the input at first flip-flop? If we put X equal to 0, A equal to 0, X equal to 0, B equal to 0, we'll get DA equal to 0. So the value of DA will be 0. So when DA is 0, in the next clock pulse triggering, what will be the next output of this D flip-flop? The next output for this D flip-flop will be 0. So this 0 will be transferred. So the next state of A will be 0. Remember, we are using D flip-flops here. Instead of D flip-flop, if we would do the same thing using JK flip-flop or RS flip-flop, then we would have two inputs here, JA, KA, JB, KB. So in this column, we were supposed to have JA, KA, JB, KB, and for each of them, we are supposed to get this type of Boolean expression for any input combinations. What is the JA value, KA value, JB value, and KB value? Based on that, next state will be determined. Here we have one input DA. Now we have another input DB for second flip-flop. When A equal to 0, B equal to 0 and X equal to 0, so what will be the value here? The value of DB will be 0. So whenever I have DB equal to 0 here, in the next clock pulse triggering, what will be the next state of B? This 0 will be transferred. So next state will be 0. With this condition, if A equal to 0, B equal to 0 and X equal to 0, what will be the value of Y here? The value of Y will be 0. If we put all the values 0 here, the value of Y will be 0. That is written here. So this is clear. Now let's go for second combination 0, 0, 1. Present state of A equal to 0, present state B equal to 0 and X input equal to 1. So what will be the value of DA? Let's put X equal to 1 but others value as 0. The value of DA will be 0, the value of DA will be 0, and the next state of A will be definitely 0. And whenever we are putting X equal to 1 and A equal to 0, so the value of A prime will be 1. So 1, 1 will give you the value of DB equal to 1, and the next state of B will be 1. What will the value of output Y? If we put 0, 0, 1 here, we'll get the value of output Y equal to 0. Similarly, we can go for the third row, that is 0, 1, 0. If we have 0, 1, 0 combinations, what will be the value of DA? 0, 1, 0. That means A equal to 0, B equal to 1, X equal to 0. That if we put those values, the value of D will be 0. And corresponding next state of A will be 0. And if we put A equal to 0, B equal to 1, X equal to 0, the value of DB will be 0. If we put 0 here, the next state of B will be 0. And if we put A equal to 0, B equal to 1, X equal to 0 in Y equation, we'll get Y equal to 1. In this way, we can construct the remaining values of this state table. So these are the corresponding values for this next state column and output column and flip-flop inputs column. Now from this state table, we can easily reproduce our state diagram. Let me repeat the procedure in brief. First of all, we need to find out the input equations for each flip-flops. Next, write all the combinations for present state and inputs. We have 8 combinations for 3-bit case. Then, for each value of present state and input case, find out the value of input in each flip-flop and put those values here in excitation column of the table. Then for those inputs of the flip-flops, figure out the value of the next state, and for each combinations of present state and input, find out the value of output Y. In this way, you keep constructing the table. Finally, you'll get this state table. Next, from this state table, produce the state diagram, which was described in our previous lectures. Next, we will start a new topic, that is sequence recognizer, or sometimes it is called sequence detector. How it works. If we see this block diagram, we can describe the operation of sequence recognizer. In this block diagram, we can see we have sequential circuit inside this box. There will be an input through which an input sequence will be sent. For example, 0, 1, 0, 1, 1, 1, 0, 0. In this way, the input sequence will be sent. Each clock pulse triggering, the inputs will be transferred through this sequential logic circuit. Now, according to the operation of sequence recognizer, the circuit will be designed in such a way the output will be 1 when the circuit gets a predefined sequence. Any input sequence may appear, but whenever circuit will get a predefined sequence, after getting that predefined sequence, the output Z will be 1. Let me give you an example to clarify the idea of operation of sequence recognizer. Suppose we will design a sequence recognizer that will detect 1101 sequence. In input sequence, we may have millions of inputs combinations, but whenever this input sequence will get 1101 sequence, the output Z will be 1 only for that case. For example, we are considering this input. First 0 is transferred, then again 0 is transferred in each clock pulse, then 1 comes, then 1 comes, then 0 comes. So whenever we'll have 1101 sequence in this input sequence, the output Z will be 1. So where do we have 1101? Here we have 1101 first sequence. After that 1101, for all these values of Z will be 0, but when it gets 1101, after the last one, the Z output should be 1. This is the requirement from this sequential circuit. Next, we have another set of 1101 here. This is the 1101. So after this 1101 sequence, then Z will be 1. For all other cases, the values of Z should be 0. Z will be 1 when it recognizes 1101 sequence. Then input keeps getting the sequence. Even though we have last one here, but another 1101 sequence is here. This is the another 1101 sequence. This one is common for both sequence. Still, it's getting 1101 sequence in another case. So after this one, the Z value should be equal to 1. In this way, it will work. Now we need to design this circuit for any input sequence. Whenever we'll have 1101, at the final one case, the Z output should be 1. For all other input sequence cases, the value of Z should be 0. So this is the operation of sequence recognizer or sequence detector that will detect a particular sequence. We'll solve this problem. For this particular problem, whenever it will detect 1101, the Z output will be 1. For all other input sequence case, the Z output will be 0. Remember, we need to have a memory that it has got 1, then second one, then third case it's getting 0, then fourth case it's getting 1. Once it gets the final one, then the output Z will be equal to 1. So at the very beginning, we need to construct the state diagram. Let's start constructing. In this circuit designing, input and outputs matter. For the time being, we'll assign states with some symbols. Suppose my present state or initial state is A. At the very beginning, the state is A. Now, whenever we have 0 inputs, being at A, whenever we have 0 input, that means I am confirmed that I am not getting 1101 input, because in order to get 1101 sequence, first input should be 1. So unless or until we get 1 for this case, the state must loop here, giving Z equal to 0. So if we have 0 input, the output should be 0 and the next state should be A. As long as X is 0, it will have a continuous loop in this state A. Next, if we get one input being at A, we need to keep it in memory. So whenever we want to keep something in memory, we'll change our state. So whenever we'll get one input being at A, we'll move to another state, that is B, and for one input equal to 1, but the Z output should be 0. Whenever we are in B state, it's confirmed that the previous value was 1. Now we have got 1, 1, and we are at B. If we get our second one, then we'll keep that in memory, and if we want to keep something in memory, we'll go to the next state, that is C state. So if we get second one, then we are at C state, and Z output should be 0 because we have got 1, 1. It's not completed yet. 1, 1. So at this moment the output should be 0. Z output should be 0. Now we are here in C. What does that mean? It means that previous two input values are 1. It's confirmed. Unless or until we get previous two values equal to 1 and 1, we cannot come to the C position. Now being at C, if we get 0 input, then we need to keep it in memory. What will happen if we get one input? I'll come to those points later on. Suppose for being at B, if we get 0 input, what will happen? We'll come to that point later on. First of all, let's see what should be done whenever I am getting the exact input sequence which we are going to detect. Now being at C, if we get 0 input, we need to keep it in memory, so we'll change our state. So we'll go to D state. If we have 0 input, and corresponding output will be 0. When we are at D state, what does it mean? It means that it's for sure we have got 1, 1, 0 input. Unless or until we get these 3 consecutive values 1, 1, 0 as input, we cannot reach to D position. Now we need to wait for one input. If we get next input as 1, what will be the next case? If we get next input as 1, the output Z must be equal to 1, because after D, if the input equal to 1, that means we have got 1, 1, 0, 1, complete this sequence. This is for sure. So output Z will be equal to 1. There is no doubt about this. But what will be the next state? In order to get the same sequence, the next state can be merged to A. That means it will start from the beginning and it will search for 1, 1, 0, 1. But if the next state is connected with A, then there is a problem. Already we have got 1, 1 from D, and if we reach here, then again if we start for this sequence, here this 1 is already there. After a single 1, if we get 0, 1, then again it's another sequence. But if it is connected with A, we must wait for 2 more ones. After this 1 plus 2 more ones, if we get 0, then it will recognize 3, 1, 0, 1, and it will give me output Z equal to 1, which is not correct. That's why instead of connecting D to A, we must ignore a step of 1 in order to get 1, 1, 0, 1 for the next case. So instead of connecting this D to A, we must connect this D to B. So if we connect this D to B, what will happen? After this 1, if we get next one, it will go to C. That means 2 ones. Then the next value, in order to recognize the sequence, will be 0. Then next value, if the next value becomes 1, then again the Z value will be 1. So it will be continued like this. So instead of connecting this D to A, we'll connect this D to B. I hope you understood why should we connect this D to B. So this D should be connected with B. Now you can check at the reset condition. If we have 1, 1, 0, 1 condition, that means A condition. If we have 1, then it will go to B. Another 1, it will go to C. another 0 it will go to D, another 1 it will go back to B and giving 1. So giving 1. If we get another 1, then it will go to C, that means 1 1 0 again 1, and the Z value will be equal to 1. So in this way it can recognize 1 1 0 1 sequence. Now still this state diagram is not completed. What will happen if being at B, if we get 0 again? In order to find out that condition, we need to understand when we'll be in B position. After getting first one, we are at B position. In the next one can be either 0 or 1. If the next value is 1, it will move to C. But if the next value is 0, then it must start from the beginning. So being at B, if we get 0 input, the B should come back to A. So B should come back to A giving Z equal to 0, because the sequence requirement is not fulfilled. Again it will search for another 1. If it gets 1, then it will go to B, searching for another 1. If it doesn't get, it will come back to A. In this way it will have a loop. Now being at C, if we get 0, it will move to D. Fine, this is our normal sequence. But being at C, what will happen if we get 1? Whenever we are in this position, C position, what does that mean? We have already got 2 1s. First one, second one. That's why we are in C position. Now if we get third one, what does that mean? We have 2 preceding ones. We may have thousands of 1 before that, but we have 2 preceding ones. That is for sure, because that's why we are at C. So we don't have to go back, because if we go back, then another extra ones will be added. Instead of going back, if we get 1 here, we'll have a loop in C giving Z equal to 0 output. So if we are in C and we are getting 1s, and if we get thousands of 1s, we will always get 2 preceding 1s. Suppose we have lot of 1s here. Even though I have thousands of 1s, last 2 1s can be recognized as my sequence, the 1s from the sequence. So after those 2 1s, if we have 0, then it will go to D position and it will continue accordingly. So in this case, if we have 1 1 and lot of 1s here, then it will have a loop here. Whenever it will receive 0 input, then keeping 2 1s in preceding side, so it will move from C to D. That will exactly give me the sequence 1 1 0 sequence. Then after reaching to D position, if it gets 1, it will go back to B and it will give Z output equal to 1. Now the last state at D, if we have D equal to 1, it will move from D to B. But what will happen if we get the next input equals to 0? If next input is 0, so we are getting 1 1 0, but after that 0. That means it's not my proper sequence. We are getting 1 1 0 3 bits correctly, but the next bit was supposed to have 1 to get our prescribed sequence, but here we are getting 0. So 1 1 0 0, but that's not our original sequence. So it must start from the beginning. So if the D is 0, then it must go back to A position giving Z output equal to 0. This will be the case. So this is the complete state diagram for the problem that was stated earlier, detecting 1 1 0 1 sequence. Now from this state diagram we can easily plot the state table as the method was described in the previous lectures. I hope you will be able to construct the state table. Before constructing the state table, you must assign bit for states. How many states are there? There are 4 states, A, B, C, D. To represent 4 states, how many state bits are required? We need 2 state bits. A equal to 0 0, B equal to 0 1, C equal to 1 0, D equal to 1 1. These 2 bits will represent complete 4 states. Now how many flip-flops should we use? As we have 2 state bits, we need to use 2 flip-flops. What type of flip-flop? We can use any type of flip-flop, JK flip-flop or D flip-flop or T flip-flop or RS flip-flop. It's up to us. Based on that, next step is to construct the excitation table from our state table. Once the excitation table is constructed, then we need to find out the Boolean expression using kernel map as described in the previous lectures. And finally, we need to construct our sequential circuit, which will be able to detect this 1101 sequence for any input cases. I hope all of you understood and all of you will be able to design this type of sequence recognizer. We are going to finish here. In the next lecture, I'll show you a bit more complicated sequence recognizer for your better understanding. Thank you for your patience hearing. Feel free to contact me if you have any question.